So here, like for a single dot constraint also, we also use folded leaf springs. And I think we have already discussed about it. So the constraint direction is along the fold line. And this is just one illustration. Suppose if you apply F in plane, it's very stiff. And mainly stiffness is because of the bending and shear. And then we try to uh, use the formulated, try to calculate the stiffness along the this direction. So if there is a force Fz applied along the fold line and Uz is the displacement, so then you talk about the stiffness in the in the constraint direction. And then you get these components. So these two components are mainly, one is because of the bending, and the other because of the shear. Mm. And shear you can consider because the it's like a short beam, so then they may come into picture. So you try to use that, and they are more or less in parallel, so you use it. And here A is the area of cross section, T times H, the width, and T is the thickness. A and B are the lengths of the folds, right? And they are used in various application. And one of the thing what I discussed with you earlier is you can design a very good planar stage, you know, which can give you displacement in x, y, and theta rotation, right? X, y directions, translation, and rotation in z direction. So, but only motion in a plane. And it's much better than three wire flexures because there is no shortening effect. So general formulation, again, just like a cantilever kind of thing. So if you have a folded leaf spring or folded structure, and if you apply forces at the end and moments, and you have displacement, corresponding displacement ux, uy, and phi, what will be the equation? So this is a generalized formulation. So it's written in terms of compliance matrix. So just inverse of a stiffness matrix here. So this side is your displacement, and the other side you have the forces acting, and connected by either stiffness matrix or compliance matrix. So here, this is the compliance matrix, right? And so this is the generalized one. Now, depending on how you attach them, your boundary condition changes, right? And for different boundary conditions, these are the standard boundary conditions usually you have, and then you can derive it from here. So this kind of questions can be asked in the exam also, like what kind of boundary condition you see. So, and based on that, can you apply, can you use it, right? So here, like, suppose if it's just moving. So I think one should be able to tell me what are the boundary conditions. If you have this kind of arrangement, what are the boundary conditions here, right? And so uh, here, can you tell me what is the boundary conditions here? What are the what are the boundary conditions you impose here in the first case? Anybody? Can you tell me? Where you attach the body with the rollers and supported in. So is they are rollers. So what does it mean? What is the boundary condition? Do you put the uh, displacement boundary condition or the force boundary conditions? Anybody? Vishnu? Mohit?
Yes,
So
sir.
just
I
answer.
think
Who is
displacement.
answering? Hmm?
So, sir, I think displacement in y direction will be not there.
Yeah. So the uy will be 0, right?
Yes, sir.
Yeah. What about fy?
So non-zero.
Yeah, yeah. So many times I think students make mistakes here. So I think try to look clearly. Huh? The forces may be If it's not given, so one is applied force, but then you may have reaction forces, reaction moments, and that you have to calculate, right? So okay, uy is 0. What about theta, phi, in a way? Can you put phi equal to 0 here? There are two rollers. It's not pivoted, right? It's a pivoted, then you can say only uy equal to 0, right? But it can move in x direction, right? Y direction, I agree, it, it doesn't move. But about phi, whether it can rotate? Can you tell me? It's a clamped, right? It's showing clamped. It's not dot there, right? So if it's a roller and at the end of the flexure, if it's a dot, then you may not have a phi there. But if it's shown like this, it means it's a clamped, right? Only moving in x direction. So your phi is also 0. Do you agree with that? In the first case. So there is no rotation at the end. Same way in this case, rotation is 0. Also, in this case, uy is there. It can move, it can slide up and down, but it cannot move horizontally. So displacement along the x direction is 0, right? Here again, it's inclined. So whatever you write, see here is written ux equal to uy, right? So displacements are related in this case. Hmm? Again, here phi is not changing. Huh? So again, phi, the boundary conditions, you have to clearly check. Hmm? And then equivalently, you should be able to reduce it to this formulation. So just work from here and try to find those relationships. Okay. So what we do, let's just stop here.